Hello, this is William M. Briggs again, and we're cutting through the noise of the science. And of course, climatology, climate science, all this kind of a thing, climate change that we've been talking about, we're going to continue talking about. And today, since so many decisions are made in the name of climate change, made by our rulers and decision makers and so forth, made for us, relying on these models, we need to really understand what these models are. We need to understand their strengths and their weaknesses. You don't often hear about the weaknesses, but there's weaknesses and there's plenty of them. And we need to see what they mean. And we need to also see what a prediction is. This is very useful, even if climatology is not your main interest, because the way these models work are pretty much the same in any science. Any way that we want to predict the future, we want to say something about how the world will be. The world meaning everything there is, the universe, everything. We want to make some observation in the world, and we use a model to say something about it. Models can be guided by various theories and all that kind of a thing, which we'll look at. So let's look at, in brief, the elements of a climate model, and then we'll see what a scenario is, and the difference between a prediction and the difference between climate models and all that kind of a thing. And we'll begin to understand the strengths and weaknesses that these models have. Okay, so here's in typical word form, here's what a climate model is. It has an enormous range of assumptions. All of these are assumptions, or in logic we would say they're premises. All the stuff that goes into a model, all right, all the things that the scientists think are important that go into the model. It's just a list of assumptions. They say, here's the way the world is, or approximately so, here's what we believe. And that stuff is stuck into the model. One of the primary things is something called fluid dynamics. Obviously, you know what the ocean is made of a fluid, mostly. Some of it is a solid in the form of ice. That is a fluid, but the atmosphere itself is a fluid. The atmosphere is treated as a fluid, and it has certain dynamical laws that are able to be deduced and show how motion can take place. They're just the laws of motion. That's easy enough. Radiative transfer. Well, obviously we get energy from the sun. That comes in various wavelengths and at various strengths. Not every wavelength that we get from the sun, some of it is in visible light we all see, but we get other light too from the sun. And we also have light that comes off of the earth. Yes, it's infrared light and so forth. That the earth radiates back out into space or back up against clouds, and clouds radiate that light back down. So we have to understand radiative transfer, and these are pretty without much controversy about how radiation bounces around and so forth. And then there's thermodynamics, and this is how temperature influences things, for instance, and temperature and water vapor and all that kind of a thing. It is here the big assumption that is made that CO2 increases temperature. This is an assumption of the model. It's an assumption about how much CO2, of an increase in CO2 increases the temperature. All right? It's an assumption built into the model. The model says if you increase CO2 by this much, you'll increase temperature by this much. Globally average temperature. Okay, we'll discuss what we mean by that later. So what we cannot do is then we run this model, we make a prediction about the world, and we say, look, if CO2 increases, temperature increases, therefore it's been confirmed. Doesn't work that way. We started with the assumption that CO2 increases will increase the temperature. If we observe, we can't then conclude from the model saying that that's what happens. If we run various scenarios where we increase the CO2 input to the model, that the temperature increases, that we're therefore allowed to say that we have verified that CO2 and temperature have a positive relationship like this. This is built into the model. We need to test whether that assumption and the strength of that association is true or not. You can't conclude from just looking at the model output that what you put into the model is true. All models, absolutely all models, only say what they're told to say. There's all sorts of coding shortcuts too. There's you can't code everything. That goes with this next thing right here. Guesses in what are called parameterizations. So we're going to have a whole separate video on this, but the climate models don't measure every point on Earth. They measure large, very large geographic regions at a time. The world is too big and the atmosphere too deep to run the model everywhere, all over the place, all at once. So there's crude means and averages taken in a way of thinking about it. And these are called parameterizations. So in a lot of these models, clouds don't exist as clouds per se, but as a parameterization. And the way the clouds work and all the assumptions that are made about how the cloud works with the incoming radiation and the upwelling radiation from the Earth and the way the water vapor works and how high the clouds are in the atmosphere and how thick they are, how opaque they are to the light, all these kind of things. While they might be well known about clouds in particular, individualized, they can't be known at the global level all at once. There's too much information, so that there's hand waving done in all of these models, and it's not clear what's the best parameterizations to use for all these kind of things. And then the important thing, the data assimilation, also what is known as the past. This is all the past data that we take in. I'm going to do an entirely separate video on this because it's crucial we understand that there's enormous limitations to this and all sorts of shortcuts that are taken that shouldn't be taken but are. So, but I'll just take this right now to meaning as the past. And it's very crucial because we don't see, I'll just give you a brief glimpse of the future, we don't see the climate. Nobody lives and sees a climate. What we do experience is the weather. Of course, right now, today it's snowing where I am and cold, but tomorrow they say maybe it's going to be a little bit warmer. So we take and average those two, the cold and a little bit warmer, and we have something tepid in between. So climate is an average of the weather that we experience, all right? So all kind of ways, there's all kind of ways you can get an average with all kinds of variability and get the exact same average, so that when we're talking about climate, we're not necessarily talking about weather. That's crucial. Okay, so that's all the list of assumptions here. Some of them are very good assumptions, like the fluid dynamics and some of the radiative transfer, and some aren't, like the CO2 relationship with temperature and these parameterizations and so forth, and especially what data that goes into the model of the past. So now that we have all of this, how do we make predictions? Let me draw this up for you. Okay, here's how it works. We have our model, just in graphical form here. We have all of those assumptions I talk about, but I'm going to separate out the past data as being somewhat different. These go into the model. And then we have a scenario. Then we have a scenario which says the future will look like this. It may be the future will look like an increase in CO2 levels in the atmosphere by so many parts per million. Whatever it is, there's some scenario. We say, here's the way the world will look. Here's the way the world will look. They're fed into this model, and using the assumptions in the past data and all that stuff, out churns a prediction. They'll say, here's the way the world will be if the scenario holds, and if the past is true, and if the assumptions are correct. That's all models are. They're all like that. If the data we used was correct, if the assumptions that we used are correct, and if the world looks like the future scenario that we posit, then here's the prediction. All right? And the prediction can be verified. We look to the world and say, if the world really was like how the scenario said it would be, if we really did increase by 10 parts per million CO2, and then we look at the prediction and we compare that prediction to the world. And if the two don't match, we know the model doesn't work. A lot of times people will say, oh, a scenario is not the same thing as a prediction, therefore we don't really care if the scenario was wrong. No, absolutely false. If the scenario said the world will be like this, and the world was like that, and the model made a prediction, and that prediction did not come true, or it wasn't close, or it was wrong in all kind of ways that we could measure, then the model's bad. We can absolutely say the model is poor and needs correcting. We can't just judging by looking at the prediction and seeing that it's off or wrong or biased or any of these kind of things tell exactly what's wrong with the model. There's all this past data and all these assumptions. Any number of things can go wrong. It could be just one thing, could be many things, but we know we need to correct these things. All right, so here's the strange thing about these models. Models feed into models, which then feed into other models, which feed into still more models and so forth. What you'll see a lot of times, and you can verify this yourself, and I'll make a separate video on this to prove it to you, but scientists have determined that every single health malady, every disease, everything that can go wrong with the human body will somehow be exacerbated, made worse by climate change. Every single disease. You can verify this yourself. I'll have a video to show you how you can verify this yourself. It's preposterous, but they do say these kind of things. And here's how they work. They take these predictions like this. They take a scenario of the future. They use these models to make a prediction. These predictions are fed into their own models, say heart disease. There are any number of papers that argue that heart disease will increase under climate change. There really are. They have their own list of assumptions. They have their own past data, which is not based on which is based on measurements of heart disease and all these kind of things, and they make their own prediction. So we have a prediction of a prediction. This prediction already has some plus or minus associated with it, but almost every time I've heard of this uncertainty that we have in this prediction is not carried forward into this prediction. It is taken as a matter of fact. And then this prediction has its own plus or minus uncertainty. So really what we have is we have plus or minus plus or minus. We should have something like 2 times plus or minus uncertainty in this final prediction of how heart disease is going to be modified by climate change and so forth. But it never is, because they ignore this uncertainty, and really they ignore the uncertainty they have of their own model right here in ways that I'm going to show you. But this is how it works. It's model based on model, and the other models come downstream. What if we change the way that we mitigate the particular climate, the way we move people around in climate, the way we could change the economy and all these kind of things? These are more models that are tacked onto these models. The uncertainty continues to grow, and I'll prove this to you. I could even do a separate video on that. It's called the multiplication of uncertainties. It's almost never accounted for. Almost never is it accounted for. But you must understand, this model is not certain. Predictions of the climate that all these sophisticated climate models make are not certain. There's uncertainty in them. They're not wrong. They're not exactly the best models in the world. They don't make skillful predictions, and I'll talk about what I mean by skillful predictions in another video too. But they're all like this. And many of these models that people use, there's great overlap. There's groups in the United States and in Europe. They have their own separate climate models, but it's not independent. Many of those assumptions are the same, like in thermodynamics and the dynamics of the fluid flow and the radiative transfer and things like this. There's different slight adjustments they make to some of those assumptions, but overall a lot of the assumptions are the same. So the models are not giving you independent evidence, but they can. There are some models that can, and they're often not used, but one that you could use yourself. In fact, you possess this model. We've talked about it before, but I'll let that go for another video. In any case, I want you to just understand this. When you see these things all the time, these headlines come once a week. Last week there was a headline, laryngeal dryness is supposed to increase under climate change. People are going to have more sore throats. This is a research paper in Nature, one of Nature's journals, showing that sore throats are going to increase because of climate change. And it worked in exactly this fashion. All right, there's just model after model after model like this, and they string them all together, and they always forget these uncertainties should at least something like, well, they multiply and become greater, and I'll show you what I mean by that. That's all for this time. I want you to understand the main thing is that all models are like this. They have past data that they assimilate into the model in some way, and that assimilation step we need to understand. And they have a list of assumptions. And then they say, here's the way the world, if the world is like this, here's what will happen. Every model in science works like that. If we understand that, then we understand better how to criticize these models and how to understand what they're telling us. That's the most crucial part about all these things. That's it for now. Thank you very much for listening. Oh, I'm supposed to ask you to click the subscribe button and like and all that kind of a thing. I know you know how to do that, but I was told it's important to remind you. So I am reminding you, and I thank you very much for all that. Thank you very much for listening. We welcome comments. I'd be happy to answer them when I can. Thank you very much.